Did you know that orange juice contains a high amount of vitamin C? But how can we determine the amount of vitamin C present in fruit juice? In this video, we will show how this process is carried out. Now, I will present our experiment on the determination of vitamin C in fruit juice using titration. First, let's talk about vitamin C. Vitamin C, also known as ascorbic acid, is an essential nutrient that our body needs for healthy growth and proper functioning. It can be found in many fruits, especially orange, lemons, and strawberries. Vitamin C plays an important role in strengthening the immune system by helping wound healing and protecting our cells from damage caused by free radicals. In this experiment, we determine the concentration of vitamin C in fruit juice by using an iodine titration method. This method allows us to measure the amount of vitamin C accurately through a chemical reaction between iodine and ascorbic acid. The results obtained can help us compare the vitamin C content in different fruit juice samples. Before discussing the experiment further, it is important to understand analytical chemistry. Analytical chemistry is a branch of chemistry that focuses on identifying and measuring the chemical substances present in a sample. It helps scientists determine what substances are present and how much of each substance exists. This field is widely used in laboratories, industries, medicine, environmental monitoring, and food quality control. In our experiment, analytical chemistry is applied through the titration technique. By measuring the volume of iodine solution needed to react completely with vitamin C, we can calculate the concentration of vitamin C in the fruit juice sample. Therefore, this experiment demonstrates how analytical chemistry can be used to obtain accurate and reliable information about the composition of food products.
Okay, so now I'm going to talk about the objective and apparatus needed. So for the objective of these experiments are to determine the vitamin C, are known as ascorbic acid, content in the fruit juice using titration. And the second one is to calculate the concentration of vitamin C present in the fruit juice sample. And the apparatus is 50 ml burette stand and clamp, 10 ml of volumetric pipette filler, 250 ml of conical flask, 100 ml of beaker, volumetric flask, measuring cylinder, funnel, wash bottle containing distilled water, and the last one is white tile.
Next, I will explain the principle of experiments for the determination of vitamin C in fruit juice using titration. This experiment uses a redox titration method. Redox stands for oxidation and reduction reaction, where electrons are transferred between substances. In this experiment, iodine acts as the oxidizing agent, while vitamin C, also known as ascorbic acid, acts as the reduction agent. The purpose of this titration is to determine the concentration of vitamin C present in the fruit juice sample. For the half equation, oxidation is C6H8O6 to C6H6O6 plus 2H plus 2E. For reduction is I2 plus 2E becomes 2I minus. Next, reaction between iodine and vitamin C occurs when vitamin C reduces iodine into iodized ions. At the same time, vitamin C becomes oxidized. This reaction continues as long as vitamin C is still present in the solution. The chemical equation for the reaction is C6H8O6 plus I2 produces C6H6O6 plus 2H plus 2I minus. Starch is used as the indicator in this experiment. The function of starch is to detect the presence of excess iodine. When iodine is present, starch forms a blue-black complex, which helps us to observe the endpoint clearly. Lastly, the endpoint of the titration is reached when all the vitamin C has completely reacted with iodine. Any extra iodine added will react with starch, producing a permanent blue-black color in the solution. Therefore, the appearance of blue-black color indicates the end of the titration and allows the amount of vitamin C in the fruit juice to be determined.
For methodology, we have 4 main steps. First is preparation of vitamin C solution. Second is standardization of solution. Third is titration of vitamin C and iodine solution. And lastly, our expected result. For the step-by-step procedure, firstly, a commercial vitamin C tablet is crushed, dissolved in distilled water, and carefully filtered into a volumetric flask. The solution is then diluted up until calibration mark. Next, an iodine solution is prepared. Because iodine has low solubility on its own, it is dissolved alongside potassium iodide to form a dark, water-soluble triiodide complex.
Finally, an sodium thiosulfate solution is prepared by dissolving the crystalline powder in distilled water, and this will be used to standardize the iodine. For the standardization step, a fixed volume of the iodine solution is titrated against the sodium thiosulfate until the dark brown color fades to a pale yellow. A starch indicator is then added, turning the solution blue-black. Titration continues dropwise until the blue color completely disappears. For the main experiment, the burette is filled with a standardized iodine solution and a measured volume of the prepared vitamin C solution is added to a clean flask. Starch indicator is introduced and the titration begins. The added iodine immediately oxidizes the vitamin C, meaning the solution remains clear as long as vitamin C is present. The exact moment all the vitamin C is consumed, the next drop of free iodine binds with the starch, creating a permanent blue-brown endpoint, and the final volume is then recorded. This is an example of result from the experiment. 3 titration trials were conducted to ensure precision. The volume of iodine solution used across the trial was recorded as 39.60 ml, 39.40 ml, and 39.50 ml respectively. From this trial, an average iodine volume of 39.50 ml is obtained. The molarity of the standardized iodine solution is given as 0.012 mol per liter, and the initial volume of vitamin C solution is 20 ml. As shown in the chemical equation, ascorbic acid react with iodine in a strict 1-to-1 stoichiometric ratio, and this means 1 mole of iodine directly oxidizes 1 mole of vitamin C. Using this value, the exact concentration and mass of vitamin C present in the commercial tablet can be successfully calculated.
In summary, the food industry relies heavily on vitamin C titration for several critical reasons. First, sourcing and raw material testing. Before a single fruit is juiced or packaged, food scientists titrate samples to check the quality of incoming crops. This helps determine if the fruit was harvested at peak ripeness. Secondly, to optimize processing conditions. As we all know, vitamin C is highly sensitive to heat, light, and oxygen. Manufacturers use titration to measure how much vitamin C is lost during pasteurization, thermal processing, or concentration, which allow them to fine-tune their methods to retain maximum nutrients. Third, shelf life studies. By titrating the same product at different intervals, companies can map out exactly how fast the vitamin degrades, which determines the best before date. Lastly, fortification verification. For products like fortified cereals, gummies, vitamins, or blended juices, titration ensures that the exact required amount of synthetic ascorbic acid was mixed in thoroughly during production. Now we move on to the importance in quality control and nutrition labeling. Quality control is all about consistency, and nutrition labeling is about legal compliance. First, consumer trust and legal compliance. Regulatory bodies like the FDA mandate that the nutrients listed on the food label must be accurate. If a juice box claims to contain 100% daily value of vitamin C, it legally must contain that amount. Titration is a validated method used to prove compliance, preventing costly lawsuits or product recalls. Secondly, standardization. A consumer expects a bottle of orange juice bought in January to taste and feel as nutritious as one bought in August. QC labs use titration daily to ensure every batch meets the company's internal standards before it leaves the factory. Lastly, to detect adulteration. Sometimes cheaper juices are mixed into premium juice to cut costs. Testing the exact ascorbic acid profile via titration helps verify the authenticity of a fruit product. In conclusion, this experiment successfully demonstrated the efficacy of iodometric titration as a precise analytical method for determining the vitamin C content in fruit samples. The experiment relied on a redox reaction where ascorbic acid was oxidized by iodines. The exact endpoint of this reaction was successfully identified using starch indicator, which produced a distinct color change the moment all the vitamin C in the sample was completely consumed. Beyond the laboratory setting, this titration technique holds immense value in the food and beverage industry. It serves as a foundational tool for quality control, allowing manufacturers to monitor nutrient degradation during fruit processing, establish accurate shelf life and expiration dates, and verify compliance with regulatory nutrition labeling standards. Ultimately, this experiment highlights how quantitative chemical analysis directly bridges the gap between laboratory science and consumer health and trust. That is all from us. Thank you for staying until the end of this video.